Alright, welcome back. We are going to continue with our chapter on acceleration, and now we're going to move on to section 2, looking at motion with constant acceleration. So we kind of already talked a little bit about acceleration, that it's the change in velocity over change in time, and now we're going to look at constant acceleration. So we can take the acceleration equation and rewrite it to solve for final velocity, given acceleration and initial velocity. So far we have taken that initial equation of acceleration equals change in velocity over change in time, and that's what we've used and solved for acceleration. But sometimes we want to solve for other variables. So basically this is just a rearrangement of the original equation. But if you want to put these other rearrangements on your card, you're more than welcome to do that also. So we know that acceleration is change in velocity, which is v final, minus v initial, over change in time. If we want to solve this equation for v final instead of acceleration, then we need to get v final on its own. Well, the way to do that first is to get rid of anything in our denominator. Since it's being divided, I would multiply, so a delta t equals v final minus v initial. And then to get v final on its own, because v initial is being subtracted, I would add. So I'm going to get v initial plus a delta t equals v final. So that's basically a rearrangement of the acceleration equation. If you want to put it on your note card, you can do that, absolutely. And now we're going to go on to finding position with constant acceleration. So we did v final, now we're going to look at position. Well, constant acceleration changes the velocity at a constant rate, because remember, acceleration is the change in velocity. And if acceleration is constant, velocity is changing at a specific constant rate. But position does not change at a constant rate. So if you remember those particle diagrams, we had, an object or a particle, and it was a little ways away, and then it got farther away, and then further away, and even further away at a specific amounts of time. So the change in distance or displacement is not constant. We can look at a position time graph and get the slope, and that's how we create a velocity time graph, because the slope is equal to the velocity, and we're going to do an example of that. A velocity time graph will give you information about displacement, because since velocity is distance over time, we rearrange that, we get that distance is velocity times time, and we know the area under a graph is equal to displacement. Let's take our velocity and our time. Let's just say we have something that looks like this. Well, since area is length times width, so here's our shape. Okay, we have this triangle shape. Length times width, or for a triangle, 1/2 base times height, so 1/2 base height, that gives us the area, which is equal to the displacement. We could also have a graph where it's velocity time, and it looks like this. So break it up into two parts, calculate the area of this shape, calculate the area of this shape, add them together, that's your displacement. Alright, so you can put this equation on your note card, and I'm also going to show you how to derive it using the velocity equation and the acceleration equation. Okay, so, whoa, what is going on here? Alright, first thing we want to do is write out what we're trying to get. So, d final equals d initial plus v initial t plus 1/2 a t squared. Alright, so we know our velocity equation is delta d over delta t, and we know our acceleration equation is delta v over delta t. Now if I take a look at what I'm trying to derive, I see that I am missing v final. So basically that's how we're going to take velocity and our acceleration equation and put them together. We're going to solve one for v final and plug it into the other one. So I think it'll be easier to solve acceleration for v final. It really doesn't matter. So I have v final minus v initial over my delta t. If I rearrange this to solve for v final, that's something we've already done. So a delta t plus v initial equals v final. So now I'm going to take that quantity, let's get a different color here, and I'm going to plug this in for the v final in this equation. And so I've got v final plus v initial over 2 is average, and that's delta d over delta t. So let's plug in our v final from the acceleration equation. So this is a delta t plus v initial, and now let's do the rest in our other colors so we can kind of keep them separate. So this is plus v initial over 2 equals delta d over delta t. So do you see this part in red was from over here? So I just took that and I plugged it right in there. So now I've substituted it out, And I'm going to go through and solve for d final. Alright, so since I want d final, I want delta d by itself. So I think what I'll do is maybe multiply this 2 to the other side and multiply delta t just to get rid of the fractions. I think makes things easier. So I have, if I multiply everything through by delta t, then I get a delta t squared plus 2v initial delta t. I just added those 2v initials. And I'm going to multiply this 2 over here, so that's 2 delta d. Well, now I'm going to divide through by that 2. I probably could have just left it there because I want delta t by itself. So I have 1/2 a delta t squared plus, well, the 2 divided by the 2 will cancel, so v initial delta t, and that's equal to delta d. And I know delta d is also equal to d final minus d initial. So if I want d final by itself, I know I have to add d initial to both sides. So I'm going to end up with d final equals d initial plus v initial t plus 1/2 a t squared, which is what I wanted. So you can derive that, and you will need to know how to derive it, but you could also just put this equation on your note card. Okay, so we've talked about displacement, we've talked about no v final, and now we're going to talk about time. So sometimes it's easier to relate position, velocity, and acceleration without including time. And this is the equation that we get when we do our derivation without time, but I'm going to show you how to do that. So again, we have average velocity is delta d over delta t, and acceleration is delta v over delta t. I want to factor one of these out for time. I'm just going to pick velocity. So delta t is equal to delta d over average velocity. I'm going to take that and plug it in for the delta t on the acceleration. So let's get a different pen color. So we have acceleration equals delta v over, now let's plug in our substituted value, over delta d over average velocity. Okay, now we'll do the rest in red. Okay, so first we've got a fraction over a fraction. Let's fix that. So we have delta v over 1 over delta d over average velocity. Remember, that delta d over average velocity just came from my time. And I substituted it. So now I'm going to multiply by the reciprocal. And so I get a equals delta v times average velocity over delta d. I can multiply my delta d to the other side. So a delta d equals change in velocity times average velocity. Trying to get v final on one side, so I'm going to break down my velocity expressions. A delta d equals v final minus v initial times v final plus v initial over 2. Now since all these are being multiplied together, I can multiply my 2 to the other side. So I get 2a delta d, and then I'm just going to multiply through both of these expressions. So I get v final squared. Let's see, let's do negative v initial times positive v initial. So minus v initial squared. And then I've got v final times v initial minus v final times v initial. So those are going to cancel, leaving me just with v final squared minus v initial squared. So then if I want to solve for v final, I add v initial squared to both sides. So v final squared equals v initial squared plus 2a delta d. Okay, and that's what I wanted. So again, you're going to need to know how to derive this on a quiz or a test, but you could also just put this equation on your note card so you didn't have to do that derivation every time you wanted to use the equation. Alright, so you are free to try these on your own, and we'll answer any questions you have in class. Okay, so here are your check for understanding questions for section 2 on motion with constant acceleration. So number 1, how do you rearrange the acceleration equation to solve for v final? Number 2, does velocity change at a constant rate if acceleration is constant? And what about position if acceleration is constant? Number 3, what's the equation to solve for displacement, or d final, if acceleration exists for an object? And the last question, what equation is used to solve acceleration problems when information about time is not available? So please give these a try. We'll discuss them in class along with your notes, and we'll also discuss the derivations to the 2 equations if anyone has questions on those. Have a good day.